Hello everyone, I hope you're doing well. In this video, we'll be solving problem 1 from chapter 4 of Introduction to Statistical Mechanics by Roger Bowley. So what we are aiming here is to upload all of these problems from this chapter. And if this is something that you want, stay tuned. Alright, you can visit Statistical Mechanics playlist to find out all those problems and their solutions. And I have uploaded problems and solutions from other chapters as well, and their derivations and conceptual videos as well. So if you really want to do that, go ahead and watch and visit that playlist. Let's quickly get started with the problem 1, which says that take 10 to the power minus 6 joule of heat from a system at a temperature of 300 Kelvin and add it to a system at 299 Kelvin. Okay, so the situation is that we have taken this amount of heat from a system whose temperature is this, and we have added this heat to another system whose temperature is 299 Kelvin. Okay, so what is the total entropy change of the two systems? So we have to find out the total entropy change in this process, and by what factor does the number of accessible states increases. So there are the two things that we have to calculate here. The first thing is total entropy change, and the second thing is number of accessible states. Let's see how we can do that. First of all, we write the data, and we are given with heat transferred, which is Q equals 10 to the power minus 6 joule. This amount of heat has been transferred, and the first body, let's say it's TA, first system, which is this, okay, its temperature be 300 Kelvin represented by TA, and let the other body be B and its temperature is 299 Kelvin. Okay, so we have two systems here, and both of these systems undergoes an entropy change, and we have to calculate their individual entropy changes, and we'll sum them up to find out the total entropy change of the system, because we are considering both of these systems. So we have to calculate their entropy changes separately, and we'll add them up to get the total entropy change of the process. So for that purpose, if we see the situation that from system A the heat has been taken, okay, so if the energy is taken from a system, it means its entropy decreases. So delta S will be negative if the entropy decreases, and that will be equals to Q by the temperature at which it was. So this amount of heat has been taken, so because it's taken from the system A, that is why it's negative, because entropy will decrease, and decrease will have a negative sign. And we can insert the value here, which is minus 10 to the power minus 6 divided by TA, which is 300 here. Let me use the calculator. Here we can see that this is the value that we have got, 3.3333 10 to the power minus 9. So delta S equals negative 3.333 multiplied 10 to the power minus 9, and that's the joule per Kelvin, joule for Q and Kelvin for temperature, so its unit would be joule per Kelvin if you don't remember that. This is the entropy change of a system A. Now let's find out the entropy change of system B. You can write here entropy change of system A is given by same wise we can do here. Since the energy is added to the system B, so its entropy will increase, and here we'll have Q added divided by the temperature at which the system B was. So Q is same 10 to the power minus 6 divided by TB, which is 299. Let's calculate it and see what the result is. 3.3448165 multiplied 10 to the power minus 9. Alright, that is delta SB. Now the total entropy change is given by change of the two systems is given by delta S total equals delta SA plus delta SB. So we can simply sum them up. Let me do this. Let us do this here. I'm taking it as positive, and we can do this here as well to ensure accuracy. So the result that we have got here is 1.11 multiplied 10 to the power minus 11. So the net entropy change equals 1.114 multiply 10 to the power minus 11 joule per Kelvin. Okay, that is the net entropy change of the system. All right, and now let's calculate the number of accessible states that has been increased. Okay, I hope that's clear to you so far. We have simply calculated the entropy change for system A, then for system B, and then we added them up and we got the total entropy change of the system. Since we have calculated the entropy change, the next thing to calculate here is the factor by which the number of accessible states increases, and for that purpose we are going to use the Boltzmann hypothesis, the Boltzmann assumption about entropy, which says that according to Boltzmann's relation for entropy, we have entropy equals Kb, which is Boltzmann constant, times natural log of Wf by Wi. Wf by Wi is the factor by which accessible states increases. So Wf by Wi is something that we need to calculate here. Delta S is the total entropy of the system. Kb is the Boltzmann constant. So that's simple. Kb comes here, natural log of Wf by Wi. Okay, or we can write it like that. Let's first insert the values here, then we'll take the entire log or we'll remove the logarithm after inserting the values. So the value we got here is 1.11 multiplied 10 to the power minus 11 divided by 1.38 multiplied 10 to the power minus 23. Value of Boltzmann constant is 1.38 multiplied 10 to the power minus 23. Okay, so that is what I did here. Let's divide them. Negative power, and we got 8.1 multiplied 10 to the power 11. 8.1 multiplied 10 to the power 11. That's the value that we got. And to remove logarithm, what we can do here is, we know that 1 is everywhere, and instead of 1 we can write natural log of e, because natural log of e is 1. Okay, so we can write it like that. And we know that everything, the coefficient of logarithm can be appeared on the power of the term that is besides logarithm, of which you are finding out the logarithm. So we can put natural log of e with power 8.1 multiplied 10 to the power 11, 10 to the power 11. So this natural log and this natural log can be cancelled out now, because there is nothing else here, and we have got Wf by Wi to be equals to e to the power 8.1 multiplied 10 to the power 11. All right, that's the result. Wf by Wi equals e to the power 8.1 multiplied 10 to the power 11. That's the number of accessible states. And you must be wondering that why you must be wondering that why I haven't calculated this on calculator like its original value. That was the value of exponential to the power this. Then let me tell you that it's a really greater huge number, and no calculator will tell you that what this value is. Okay, so we express such bigger values in this way. Okay, that's the final answer because it's a really bigger number. 8.1 multiplied 10 to the power 11 is a really huge number, and exponent of such a greater positive number is a very big number. You can't imagine how big it is. So that is why that's the final form of the answer, and you can get this form using this method, because calculator will not give you the final result in this form like exponent power this. Okay, they'll show you error that is a huge number and they cannot calculate it or show it on the calculator. So that is why you have to do this thing, and you will see this form later in other problems as well. So that's the final answer. This is the factor by which the accessible states has increased. This is the final accessible states and this is initial accessible states. So the factor by which they increase is given by dividing the final accessible states by initial accessible states, and we can see here that the accessible states has increased dramatically. Okay, this is a huge number. So yeah, that is it for this video, and we'll meet you in next problem.